All right, let's get back to it. In our discussion of thinking backwards from alpha, beta unsaturated carbonyl compounds or beta hydroxycarbonyl compounds, we did this example where we noticed that this cyclohexenone ring could have come from this precursor in which one side was the enolate and the other side was the carbonyl electrophile. And without even noticing it, what we had done is think backwards through what's called an intramolecular aldol reaction. An intramolecular aldol reaction is one in which you have both the enolate and the electrophile carbonyl compound in the same molecule. And it was decently okay to think backwards through this reaction, but in thinking through this reaction in the forward direction, some interesting problems present themselves. First, I've just redrawn this precursor that we did from the last hour in this way. And I did that by counting carbons. Counting carbons is your friend when you're trying to avoid making mistakes. I suspect that a fair number of you would probably not have looked at this molecule and then looked at that and thought that they were related to each other or were the same thing. We're just rotating around carbon-carbon bonds to change the shape of the molecule to get things sort of to where you can see where they might have come from. If I were going to do an intramolecular aldol reaction, thinking about this in the forward direction, I got a problem. And that is, I need to use one of these as my enolate and the other as the electrophile. Now, it just so happens that there's mirror plane symmetry here. Those two carbonyls are identical. So it does not matter which one I choose to be the enolate and which one I choose to be the electrophile. However, there is a problem when it comes to which enolate I should make, because I have two different alpha carbons and two different alpha protons. So let's just, and we're using a base which is OH minus. Now, of course, two things to remember. The aldol reaction is an equilibrium reaction, which means you're going to get the most stable product. Based on what we did in chapter 17 with enolate alkylation, some of you are going to be worried about, okay, this is a base that can only incompletely deprotonate the alpha proton, so I want to make the most stable enolate. And that was true for enolate alkylation, where the stability of the enolate was what mattered, because the subsequent step, alkylation, was irreversible. For the aldol reaction, the enolate is just one intermediate along a whole set of a whole set of steps, which are all reversible. So it turns out that what matters here is not which enolate is most stable, but which product is most stable. So I want us to consider together the products that would form if we remove the purple alpha proton and if we remove the orange alpha proton. So let's remove the purple alpha proton. That's going to give us the following enolate with a negative charge on the purple alpha carbon. I'm going to continue numbering the atoms in gray. And then here, if I were to remove the orange alpha proton, I'm going to make this enolate. Again, the numbers are going to be helpful to us, especially anytime you might make a 6-membered ring. All right, let's do the intramolecular aldol reaction from the purple enolate. This is going to be alpha carbon attacks carbonyl carbon to get a tetrahedral intermediate. So I'm going to make a bond between carbon 3 and 6. Notice that 3 and 6 are already bonded to each other. So I just made a ring. Don't worry, that which we persisted doing gets easier. So what size ring did I make? How many atoms are in the ring? 3, 4, 5, and 6. That's 4 atoms. I guess we should have started numbering 1 on carbon 3. Anyway, we'll figure it out. 1, 2, 3, 4. So we just made a 4-membered ring. So start by drawing a square. Then you can number the atoms of the ring any way you want. Let's choose 6, 5, 4, and 3. Then we look at what 6 was attached to. 6 used to be the carbonyl carbon of the electrophile. It's going to be the tetrahedral intermediate carbon with a negatively charged oxygen, and then here's carbon 7. What did carbon 3 used to have? Well, it used to be bonded to carbon 4, and it is, but it also needs to be bonded to carbon 2, and 1. That makes sense? Okay. And then if we proceed through the aldol reaction, we could draw as products either this beta hydroxy carbonyl compound or the corresponding alpha beta unsaturated carbonyl compound. Okay, that's the aldol product that we get if we remove the purple beta proton. Now let's do the same for removing the orange beta proton. Carbon 1 now attacks carbon 6. That's going to give us a 6-membered ring product. Let's choose this one to be 6, 5, 4, 3, 2, and 1. The bond that we made, the new bond, is the one between 1 and 6. 6 used to be attached to, is still attached to carbon 7, and it used to be attached to the carbonyl carbon. It's now a negatively charged oxygen in our tetrahedral intermediate. 2 used to be attached to carbon 1, and 2 has a carbonyl on it. So that's the aldol, that's the tetrahedral intermediate. We protonate on the OH group, and we end up with this beta hydroxy carbonyl compound. And then if we deprotonate, if we do the E1CB reaction to dehydrate, we get this alpha beta unsaturated carbonyl compound. So we have 2 possibilities. Everything's in equilibrium. The only thing that matters is which is the more stable product. The 6-membered ring is more stable than the 4-membered ring because of ring strain. So this is the major product. And by this I mean, either the alpha beta unsaturated or the beta hydroxy carbonyl compound. In other words, in a predict the products question, you need to be able to reason through that and know that this is the desired product. Yeah? Double bond between 5 and 6. You mean here? The answer is no, and the reason for that is twofold. First, remember the mechanism of dehydration requires deprotonation first because OH minus is a bad leaving group. The alpha proton here is much more acidic than this proton there because it's adjacent to the carbonyl. Then the second reason is that this elimination product is conjugated more stable than the alternative. Yeah, and then you? Same question? Okay, yep. Remember that in the dehydration reaction for the aldol, the double bond is always between alpha and beta carbons. Okay, yes?
You might be looking too far ahead, but wouldn't both those alpha beta unsaturated carbons be Michael acceptors for a further Michael reaction?
Sure, so both of these, you're pointing out that the product of the aldol reaction is, sorry, I erased something because I didn't like my penmanship, and now suddenly I'm having to rewrite it again. That's silly. More stable, less ring strain. Yes, this aldol product itself is an electrophile in conjugate addition reactions where nucleophiles can attack the beta carbon. The last reaction we will learn in this chapter is an example of that kind of thing, but we're not there yet. Okay, intramolecular aldol reaction. Moral of the story is, don't despair, even if you've got multiple alpha protons, make the most stable ring. Okay, other questions? All right, we're gonna make the world all kinds of worse now, because everything we've done so far with the aldol reaction has been an example of what's called the self-aldol, where we make an enolate and then it reacts with its conjugate acid, the carbonyl compound. So you end up with a product where both the purple thing and the orange thing came from the same starting material. Of course, you can get bored real quickly just doing those kinds of things. So what about the cross-aldol reaction? Can we do a reaction where we try to bring together two different carbonyl compounds, and we want to use one as the enolate and the other as the electrophile? So let's just be as boring as we can be. All right, that's almost the self-aldol reaction. We've just added another methyl group. I'm going to label one orange and the other purple. And suppose we just do this reaction under basic aqueous conditions and we hope for the best. Well, under those conditions, you're going to form both enolates. You know what, I made this problem worse than it needs to be. Let's just go to both of them being aldehydes, if that's okay. I was just about to unleash all kinds of horror upon you by what I did there, and I don't want to do that. So we've got two aldehydes, two possible enolates, and you've got all sorts of potential cross-reactivity, right? This enolate could attack either of those carbonyl compounds. This enolate could attack either of those carbonyl compounds. So what you expect is a horrific mixture of products where you have the cross-aldol product of the orange enolate attacking the purple carbonyl compound, or where the orange enolate attacks the orange carbonyl compound. I'm just going to see if I can keep this straight. Or you have the purple enolate attacking the orange, the purple, let's go purple carbonyl compound. or you have the purple enolate having attacked the orange carbonyl compound. And friends, it gets worse than that, because I could have also drawn the 4 other alpha beta unsaturated carbonyl compounds. I left it here just beta hydroxycarbonyls, but it would be also fun to draw the others. In other words, we get a mess. So the attempts to do the cross aldol in this way, especially when you're using carbonyl compounds who have very similar alpha proton pKa's, generally not a good idea. So we need a workaround to do the cross aldol reaction. And there are a couple of strategies for this that are discussed in your text, and we'll talk about each of them. The first is sort of the no-brainer method, which is use as an electrophile a carbonyl compound that lacks alpha protons. Duh. So as an example of a crossed aldol in this way, let's react this ketone with this aldehyde. This is benzaldehyde, and significantly there are no alpha protons. So you hope for the best that by putting this under basic aqueous conditions, you're going to make some of the enolate, and then that enolate, you're going to hope for preferential reactivity of that enolate with the aldehyde. Now probably you're hopeful to use this same electrophile that has no alpha protons. You probably hope that that electrophile is more electrophilic than your ketone. You're still going to worry about the potential for this enolate to react with the purple ketone. But you're hopeful to get this beta hydroxycarbonyl compound and the associated alpha beta unsaturated carbonyl compound as major products. And for the most part, I think you're free to hope that this works. I would still, in this case, worry about undesired self-aldol reactivity. In other words, I would worry about the ketone enolate reacting with ketone to give you those self-aldol products. But that's one workaround you can use if you want to do the cross-aldol reaction. Yeah?
I might be looking way too far ahead, but isn't that benzene ring susceptible to electrophilic aromatic substitution as well?
Can you do things with the benzene ring? Yeah, that's chapter 20. So that's next Wednesday.
But is that still definitely like...
And normally to get benzene rings to attack, you need much more strenuous conditions than just this. So no, it's not going to interfere with this reaction. Okay, others? Okay, a second slightly less no-brainer option is to use as a nucleophile a carbonyl compound with very acidic alpha protons, so there's no question as to which enolate you form. So this is making a guaranteed enolate. An example of this might be for this beta diketone, which has a proton that's alpha to 2 carbonyls, a pKa of 9. And then in the same reaction mixture, you could have acetone, which has a pKa of its alpha proton of 20. There, it's no contest. You're not going to form any of the orange enolate. You're going to form exclusively the purple enolate because it's easy to remove the alpha proton. Having done that, and by the way, you do this in 100% quantitative yield, at that point, that's because OH minus is a good enough base to remove that proton. Remember, the pKa of water is 16, and you know how to judge how efficient and effective acid-base steps are based on pKa comparisons. At that stage, there's no contest at all. The only thing that can happen is the cross-aldol reaction to give you the desired aldol products. I'm not going to draw those. We're focusing on strategy here. You can go back through, and it would be a good, fun predict products question as you're going through your notes to draw what those aldol products should be. Okay, the final strategy for crossed aldol reactions is sort of a version of step 2, only we're going to, a version of option 3, only we're going to use LDA to 100% make one enolate first. And this is called the directed aldol. So the idea here is that the 2 carbonyl compounds never see each other directly. You use LDA, and remember this is our super strong base that can 100% remove alpha protons. We're going to use non-aqueous, non-protic solvents because we don't want to reprotonate the enolate at all. We just want to make it in 100% yield. Again, if you're wondering why this is 100% yield, all you have to do is compare the pKa of the LDA proton after it removes a proton with the pKa of the alpha proton, and that's 100% yield. And then, and only then, in a second step, do you introduce another reactive partner, let's say this aldehyde. This aldehyde actually has an alpha proton on it. And you do this reaction at really low temperature. You do it under really low temperature to avoid proton exchange between this enolate and your electrophile. If you're not careful, it's possible for the enolate in purple to remove the alpha proton from the electrophile, and then you got the same cross-aldol problem that you always had. But if you're careful, you can hope to get the desired aldol product, which would look like this. And then, of course, the associated alpha-beta unsaturated carbonyl product as well. This is the beta-hydroxycarbonyl compound. Okay, so those are 3 strategies for the cross-aldol reaction. The first 2 are first one is sort of use one partner that lacks alpha protons. That's not going to apply if you need a product that's not like this. You can use as a nucleophile a carbonyl with very acidic alpha protons. Again, that may not apply if you don't want products that have these kinds of functional groups in them. Perhaps the most broadly applicable is the directed aldol, where you use LDA to make the desired enolate in 100% yield, and then you do the aldol reaction. You got to keep it cold to avoid proton exchange. If you're using LDA, all that you've learned so far about making the less substituted enolate would apply. And your text may give you a chance to do some reactions where that is an issue. Yes? Could you do it with formaldehyde? Sure. You could use formaldehyde as an electrophile. So that would fall in the strategy of using an electrophile with no alpha protons. Yep, good. Others? All right. So in this class, we just keep on making it worse because we learn something and then we learn more things. And you're never done. Welcome to the rest of your life. You will never be done. There will always be more to learn. And as I showed you with the reviews on my paper last week, even when you think you're done, there's always more to do. Brandon Sanderson fans out there, what is it that Kelsier says? There's always another secret. Is that right? Nobody's heard that one? Okay, well, I'm not surprised that my Star Wars references land better than Brandon Sanderson references, but we'll do our best. Okay, I guess I saw a headline that the 5th book in the Stormlight Archive is supposed to drop this fall, which gives me only a few months to reread all the other books in the Stormlight Archive so I can tell what the heck's going on. Looking forward to it, but that's a lot of rereading to do. At this stage, I'm like, there was a guy named Dalinar. Who is he? Might be important. Okay, we're wasting valuable time. So the next set of reactions we're going to learn in this chapter are very much like the aldol reaction. They're going to involve enolates, but the electrophiles are going to be esters or things with leaving groups rather than ketones or aldehydes, which lack leaving groups. This is going to have an entirely predictable outcome, so I don't want you to think of what we're going to talk about now as separate from the aldol reaction. It's just sort of the ester or leaving group version of the aldol reaction. So this is going to be called the Claisen reaction. It's just, as I said, the ester or leaving group version of the aldol. The products are going to be different from the aldol, but in entirely predictable ways. So let's imagine using an ester as our starting material. We'll start out simple like we did with the aldol, the self-Claisen reaction in the same way that we did the self-aldol reaction. Now the pKa of the ester proton is around 25. So esters are less acidic than aldehydes or ketones. We need a base to remove the alpha proton. Is that a good choice for a base to remove the alpha proton? Why not? It's not such an issue of the fact that it can't 100% remove the alpha proton. That was also an issue with the aldol reaction. Scrolling back to the aldol, do you remember I said when we used OH minus, we would form some of this hydrate, but there wasn't anything that could happen to it. We get the hydrate if the OH minus attacks the carbonyl carbon. Now, fast forwarding down to the world of esters, what happens if OH minus attacks the carbonyl carbon instead of the alpha proton? Yeah. Suddenly we get that intermediate. Suddenly we just did a saponification reaction, and the leaving group, ethoxide, deprotonates the carboxylic acid, and we just fell into a thermodynamic hole that we can't get out of. Using OH minus is a really bad choice for the ester version of the aldol, because of the competing undesired nucleophilic acyl substitution reaction. So we got a solution for this, and it's as simple as modifying what the base is. If I match the base to the group that's on the ester, that is, if I use this alkoxide base, sodium ethoxide, that will sometimes be written NaOET. You could also draw it like this. Sodium is just the counter ion. Then if, instead of removing the alpha proton, if instead my base attacks the carbonyl carbon, who cares? Doesn't matter. You can't even tell, because electrons kick down and kick off an ethoxy group, and you're left with the starting material. So you're going to have a question at some point during the Claisen reaction when we're reacting with these ethyl esters. Why are we always using sodium ethoxide? This is why. So that the undesired nucleophilic acyl substitution reaction is going on in the background, but it's entirely silent and entirely inconsequential. Okay. With that as, so the idea, I'm trying to draw, there we go. The idea here is we're going to use a base that matches the OR group on the ester so that nucleophilic acyl substitution reaction is silent. Can't tell that it's happening. All right, with that in mind, let's make the enolate. Again, use of ethoxide as a base with a alpha proton whose pKa is 25 isn't going to make very much enolate at all. So, you know, it's going to make way less than 1%, and more than 99% of our material is going to be the ester. Here's the enolate of the ester. So when we do the Claisen reaction, we're going to have the enolate attack the ester. Attack the carbonyl carbon, get a tetrahedral intermediate. That's exactly the same as the aldol reaction. The only difference is going to be in the structure of this tetrahedral intermediate. Here's the new bond we made between the enolate and the ester. But the point is that on this enolate, here's, I'll label our product carbonyl carbon, alpha carbon, and beta carbon. The point is that the ester comes with this ready-made leaving group. Not a great leaving group, but a decent leaving group relative to the negatively charged oxygen of the tetrahedral intermediate. So now electrons kick down and leaving group leaves. And we make this beta keto ester. This is no longer a beta hydroxy carbonyl compound. It's a beta keto ester. And something now happens which didn't happen, well, couldn't have happened in the aldol reaction. Now that we've made this beta keto ester, this alpha proton is now relatively acidic. In fact, I think if we looked at the pKa table in chapter 17, I think this was around 13. And look at what the leaving group that left was after this ester reaction, after this carbon-carbon bond forming reaction. It was ethoxide, which is definitely a strong enough base to remove this proton. That step is downhill and effectively irreversible while the reaction is going. So the reaction is complete when we make the conjugate base of our beta keto ester. By the time we get here, there's no starting material left. And there we stay until aqueous workup. So I think on the mechanism of this reaction, your text maybe shows this, and then at this stage they show acid protonating that alpha carbon. And you're like, where did the acid come from? I thought this was under basic conditions. What we're doing here is just showing that there's mild acidic aqueous workup. We need to add acid to get the pH below 13 so that we can protonate that alpha carbon to get to the desired beta keto ester product. Some of you are probably thinking, if we end up there, why didn't we just stop here and call it good? And the answer is we could have done, but that's not actually physically what's happening. When the leaving group leaves, it's a strong enough base to remove that proton, and that's what pulls the reaction forward. All right, so that is the Claisen reaction. As before, you need to get good at looking at Claisen products and thinking about what the starting materials would have been. The Claisen product is a beta keto ester. So identify the carbonyl carbon, the alpha carbon, the beta carbon. In orange used to be our electrophile. In purple used to be our nucleophile, and in red is the new carbon-carbon bond you made in the Claisen reaction. You know, what used to be, and so you need to get good at looking at that and thinking backwards. Okay, if it was a Claisen reaction, then the orange thing used to be attached to an ester oxygen, and then the purple thing used to be the enolate. In this case, because this is a self-Claisen reaction, the enolate ultimately came from this starting material as well. All right. Anything more on that? I'm thirsty today. All right, let's think backwards. I'm gonna show you a Claisen product, and then you got to think backwards to what the starting material was. You can recognize that as a Claisen product because it is a beta keto ester. So identify the carbonyl carbon, the alpha carbon, and the beta carbon. The bond between alpha and beta carbons is the one that you made in the Claisen reaction. The orange side used to be the electrophile. The purple side used to be the enolate. So if we think back, and you'll get good at going directly back to starting materials, but if we do this incrementally, the immediate precursor to the beta keto ester is the tetrahedral intermediate. This is the one in which the beta carbon has a negatively charged oxygen and the ethoxide leaving group is still there. Then the immediate precursor to that is where we haven't yet formed the bond between the alpha and the beta carbons. So the orange stuff is going to have been our electrophile, and the purple thing will have been our enolate. So I'll draw that here. Trying to keep things all sort of in the same spatial orientation. Carbonyl carbon, alpha carbon. This is going to be our beta carbon. And at this stage, if I want, I can start counting carbons to make sure I get the length of the chain right. Ultimately, this would have come from a 6-carbon chain. With esters on carbons 1 and 6. Okay? What we did actually was think backwards through an intramolecular Claisen reaction, going from this product, this starting material to this product is an example of an intramolecular Claisen reaction. In the text, I think that's given a name. It's called the Dieckmann condensation, but you don't necessarily need to know that name, and the name may not help you. It's simply an intramolecular Claisen reaction. So what you should do at this point is practice the Claisen mechanism by drawing it, starting with this starting material, till you get to the beta ketoester product. All right, that's all we have time for today. So have a good Wednesday, and I'll see you Friday.